You can integrate and differentiate power series? What? If we wanted to go through and make a power series for 1 over 1 minus x to the fourth using 1 over 1 minus x. What's next? Well, we want a power series, so the power series for f of x is the sum k equals none to everything x to the k. Okay, where's that come from? The geometric. Yeah. But yeah, it's a power series, it's known. How are we going to get 1 over 1 minus x to look like 1 over 1 minus x to the fourth? Some of y'all think it's integration. No, it's differentiation. And we do that derivative. How does that go? You take that and you rewind it back. It's ludicrous. Followed by the power rule. Now, that should have been positive. Yeah, because the power rule, no, the chain rule would have made it positive. So now we keep on keeping on, because one of the things that we're trying to get out of this is the differentiation of a series. We're going to zip it up. Bam, that's not 11. Just get rid of that. Okay, yeah, so it's ludicrous. Take that and rewind it back. I drop that k, and then I get that k minus 1. Now, when you integrate power series, you gain a term, a plus c. When we differentiate a power series, we lose a term because our constant's going to go away. Because the derivative of a constant is 0, so I ain't even gonna put that there. So now we started at k equals 1. That's kind of important. The index changed because we lost the term with differentiation. Now we see that we gained an exponentiation. We gained that. We're trying to get to there. So let's do it again. The second derivative, that's going to be Okay. So now we're up to 3. That's good. We're trying to get to 4. But we stick with our plan and we differentiate the series too. So differentiating the series, we're looking at f prime prime. That's the sum k times k minus 1. That's x to the k minus 2. Ooh. And we lose another term in our index. It's the derivative. Take that, rewind it back. K minus 1 is minus 2. Now, what? We got to the third. Let's try to get to the fourth with the third derivative. And it did what we wanted. We're almost to g of x, but we need to get the series that's going to represent g of x. And we take the third derivative of our series, take that, and rewind it back. That's why I have my x to the k minus 3. Oh, now what? I want my index to start at 0, because that's nice. It's clean. So I need to subtract a 3 from the index. If I subtract a 3 from the index, I need to add a 3 to all the k's in the sequence. So let me make some room. Let me make some room. Sweet animation. And I do my arithmetic. We're looking at the third derivative of x. That's going to be equal to the sum k equals 0 to infinity. Okay, because k plus 3 is k plus 3. K minus 1 plus 3 is k plus 2. K minus 2 plus 3 is k plus 1. And then x to the k minus 3 plus 3 is just k. Okay, so now I'm looking for my relationship. Me and my math got this relationship. We see this is going to be 1/6 of the third derivative of x. Why? Because how am I going to make this equal to that? You're going to have to do 1/6 of this to equal that. So that is why I have 1/6 of f prime prime prime. That's going to be g of x. Let me make some room. Clear the house. Just get in there. That's why I have 1/6 of my series that's represented by f prime prime prime. Let me just write a little faster. Faster, faster. Damn. Now you should use the ratio test. Set it less than 1. Find the endpoints, test the endpoints, and get your interval of convergence, which just happens to be -1 is smaller than or equal to x, which is smaller than 1.